In today's lesson, we will be learning about acids and bases. As always, please make sure you are watching this on either your phone or your computer so it is easier for you to take notes on your iPad. For this lesson, we actually do an inquiry lab, which is where students work with acids and bases to determine their properties rather than being given the information first. They are using the lab to determine the properties. So if you were absent in class today, I would recommend that you go watch the acid-base makeup video and work on the lab through that, and then come back and continue on with the notes. Here are some basic properties of acids and bases. One of the key things with acids is that they have a low pH. So our pH scale runs from 1 to 14, with 7 being in the middle, 7 being considered neutral. So acids have a lower pH. That means they are anything that is lower than 7 on the pH scale. pH paper will turn red, as you saw in the lab, when touched with an acid. This PHTH is or whatever that's here, that stands for phenolphthalein. So when phenolphthalein is placed into an acid, it will remain clear. When acids react with metals, such as zinc or magnesium, they will produce this hydrogen gas, which means that this is actually a single replacement reaction. Generally, they will burn the skin or make your skin itchy or red, and then they ionize water, producing these H3O plus ions, because you'll notice that this is a water that has gained one more hydrogen. Bases, on the other hand, have a high pH. That is, they have a pH that is above 7. So they will be somewhere on this side of the pH scale. They will turn pH paper blue. When base is present in phenolphthalein, it produces a bright pink color, and they are not very reactive with metals. Some of them are with certain metals, but for the most part they're not as reactive with metals as acids are. They will feel soapy or slippery on your skin, and this is because if you know what lye is oftentimes considered NaOH or potassium hydroxide, so sodium hydroxide or potassium hydroxide, and is one of the main ingredients in soap, which is why it will feel soapy or slippery on your skin. And then it dissociates in water, meaning it breaks apart in water and produces these OH ions. So you'll notice one of the big things with acids, and we'll talk about this in upcoming slides, is the acids that we've seen have been like HCl, or in the lab today we saw acetic acid, which is HC2H3O2. And you'll notice that each of these starts with that H. It starts with a hydrogen. So acids break apart into these hydrogens and then these other ions, whereas bases end with these OH. They produce these hydroxide ions. So those are the key differences between acids and bases. This slide just gives you some examples of acids and bases. One way that I like to remember it is I like to think of it like going through the alphabet. So here on your pH scale you can say it's either 0 or 1. On our pH scale it runs from 1 to 14. Well, I like to just think of it like the alphabet, where acids are A and bases are B, and it just kind of goes down the alphabet. So acids have that lower pH, whereas bases, on the other hand, have a higher pH. So examples of acids, and you've heard of battery acid, they all have lower pH. So battery acid is around a 1, lemon juice sits around a 2, and so on. Milk is actually slightly acidic, coming in at around a pH of 6. Water is generally considered to be more neutral, around that 7, and again we'll talk about that in upcoming slides. Whereas some basic things, lye is very basic, as I talked about previously. Ammonia is also very basic, meaning they have a higher pH or a higher concentration of OH ions, and the acids have higher concentrations of these hydrogen ions. On this slide we're going to talk more about what an acid is and how they work. So here, acids are ionic compounds that donate a hydrogen in a reaction. So again, before I mentioned where they start with that hydrogen, that is because they're giving up those hydrogens, and that's what makes them acidic. One thing that might seem confusing to you is before we always talked about how an ionic compound was a metal plus a nonmetal. Well, you'll notice now that even though that this is hydrogen, a nonmetal, and chlorine, a nonmetal, they're bonded together, and I am calling it an ionic bond. That is because before we were simplifying everything, when realistically there are many types of bonds. Specifically, a lot of times there's what's called polar covalent, nonpolar covalent, and ionic bonds. And this is the reason that if you look on your periodic table, hydrogen always falls. It was always kind of that weird one there. Over here by itself, it was the only nonmetal over here, and that's because it has properties similar to metals, and this is one of the reasons why. So even though this is a nonmetal and nonmetal, it is actually an ionic bond in this case. And the reason that that's important is, remember, we always said covalent bonds don't break apart in water, whereas these ionic bonds do. So when hydrochloric acid, when this is dissolved in water, what you actually have are these hydrogen ions floating around and these chlorine ions floating around in solution, meaning that they are aqueous. So if I were to draw this out, what's happening in that beaker in the solution is we have all of these hydrogen ions just kind of floating around in there, thinking back a few units when we used to do this, and we also have chlorine ions floating around in there, and they are dissolved in that water. So it is important to note that this is an ionic bond, and ionic bonds break apart into ions, whereas if this were a covalent bond like we had previously learned, it would not break apart into water, and instead inside of the beaker we would have these hydrogens and these HCl's just bonded together, and then the reactions would not occur. They wouldn't really be acidic or basic or anything because they would be stuck together as compounds, just like sugar is in water. The same concepts also hold true for bases. So a base is something that donates these hydroxide ions, which is why I showed you before they end in OH, such as sodium hydroxide. So here, these are breaking apart. Now these are more obviously ionic because they contain metals such as sodium. So this is also going to be aqueous when they're in solution, which means that they're broken apart into their aqueous states. And so those ions are broken apart, and in your beaker you would have all of these sodiums floating around and these hydroxide ions floating around, and it's those hydroxide ions that make something basic. That's the definition of a base. And then down here you just kind of see your generic equations for acids and bases. So it is some sort of hydrogen plus something else, and your base plus your hydroxide, and they are going to produce water, which is one of the key parts, plus then A and B are now going to be paired together. And I'll show you an example of this reaction later. But remember, anytime you have an acid-base reaction, it is forming water plus some form of salt. It will always be a salt because salt is a generic term for some sort of, basically for an ionic compound. And the reaction that you see down here is you have hydrochloric acid, so one of the super strong acids, reacting with sodium hydroxide, one of the super strong bases, and you'll notice we're producing water, and that's just our regular table salt. So when you mix a really strong acid and a really strong base, you're just producing salty water. On the next two slides, we're going to look at the differences between acids and bases. On this slide, we're going to focus on acids. So an acid, again, is a substance that produces H plus or H3O plus ions when dissolved. So here's an example of a reaction where HCl and water are mixed together, which any HCl that you have is dissolved in water. You're not going to have pure HCl, but you can have higher concentrations of HCl, and that goes back to our molarity. Where if you have a 1 molar solution, it's a fairly low concentration, but if you have something like a 12 molarity, that's a pretty high concentration of hydrochloric acid dissolved in water. So anyway, what that looks like in this reaction is HCl plus water, and the hydrochloric acid is broken apart into these hydrogen ions and these chlorine ions, and you have water. Sometimes instead of H plus and H2O, it'll actually just be H3O plus. And then you'll have these chlorine ions floating around. So some of the hydrogen will actually react with water, and you'll also have some H3O plus in there. So they're all just kind of swimming around in the solution. But realistically, in there, in your beaker, you would have H plus, you'll have some H3O plus, and you will also have some chlorine, and then you will also still have your water in there. So all of them will exist, and reactions are constantly occurring. These atoms, molecules, ions are constantly floating around and reacting with one another. So there are some strong acids and some weak acids. So strong acids are ones that dissociate completely or almost completely in water. That is, we have this single arrow showing that it breaks apart into hydrogen ions and chlorine ions. Weak acids are represented by this double arrow. That's because these acids just don't dissociate well in water. They don't break apart that well in water. So what's happening is the reaction is constantly going both ways. H3PO4 or phosphoric acid is breaking apart into those hydrogen ions and those phosphate ions, but also the reaction is occurring the other way, where the phosphate ions here are reacting with hydrogen ions and they're actually producing phosphoric acid. So this is said to be a weak acid when that reaction is kind of going back and forth. On this slide we're going to talk about bases. So bases, remember, are substances that produce OH ions when dissolved. So an example of this is going to be when sodium hydroxide breaks apart into sodium and hydroxide ions. Realistically, I could show this with being plus H2O like we did on the last slide, and then plus H2O. And remember, water is the only thing we will ever label as liquid in here. A strong base, similar to a strong acid, is one that produces a lot of hydroxide ions now instead of hydrogen ions. So something that breaks apart completely and will just remain in solution as a bunch of sodiums floating around and a bunch of hydroxides floating around, and then you have your water in there, is going to be a strong base. A weak base, again, is represented by these double arrows, where magnesium hydroxide is breaking apart into magnesium and hydroxide ions, but also those magnesium hydroxides are going to find each other and produce magnesium hydroxide again. So some of it's always dissolving, but then it's also being recreated. As I mentioned before, on your pH scale it runs from 1 to 14, or sometimes you'll see where it runs to 0. Either way, 7 is what's considered neutral on the pH scale. Well, water, as I told you before, is one of the few things that's considered to be neutral. The reason that water is neutral is because if you think about that H2O that we often write water as, that can be rewritten as this HOH there. And if you'll notice, this has the H of an acid starting, and it also has the OH of a base at its ending. So it is the perfect combination of an acid and of a base. And when you meet those in the middle, you are going to get your neutral water. So water realistically is always kind of breaking apart or dissociating in a beaker as hydrogen ions and hydroxide ions. But a lot of those will then form back together to creating water, and then they'll break apart into hydrogen ions and hydroxide ions, and you just kind of always have this mix. So even in a glass of pure water, realistically you have some hydroxides in there, you have some hydrogen ions in there, and you probably have some of the H3O ions in there as well. But for the most part, when you average it out, you're going to have your plain water in that beaker in your glass. Anytime we react an acid with a base, it is called a neutralization reaction. So that is when an acid and base react, producing a salt plus water, as I told you earlier. Remember, salt is basically just an ionic compound. So that is some sort of ionic compound, and then they produce water. And you can see that down here. So salt is ionic because we have metal sodium reacting with our anion of sulfate, and that produces H2O. With these reactions, they are using an equation that should look familiar to you from yesterday. Instead of being M1V1 equals M2V2, it is now MAVA equals MBVB. And this is saying Well, how much acid do we need to neutralize how much base? Neutralizing meaning we reach that pH of 7 where the solution is no longer acidic and it is no longer basic. So if we focus on this reaction here where we have sulfuric acid reacting with sodium hydroxide, that is going to produce our salt, which our salt in this case is going to be sodium sulfate plus water. So here if we do the complete ionic equation, remember, and I know this is thinking back a few units, complete ionic equation is when we write the ions of each aqueous solution. So here, H2SO4, since that is aqueous, breaks apart into its hydrogen ions and its sulfate ions. So that means we are going to have 2 hydrogen ions, and they are in their aqueous state, so we always have to indicate how many we have, their charge and their state of matter, and that is going to be plus, and there are sulfate ions, 2 minus charge, and they are the aqueous state. Plus, now we need to focus on the ions in our sodium hydroxide, which in this case are sodium and hydroxide, so plus 2 NAs with a plus 1 charge, and they are aqueous. Plus, we also have hydroxides in there. Oh, I should say we have 2 hydroxides in there with a negative charge, and they are also in aqueous state. Now looking at our products, we have our 2 sodiums still. So we have 2 sodiums with a positive charge, and they're aqueous, because remember our state of matter carries through to both of these. That means they're floating around in the solution. Plus we have our sulfate still, and they're aqueous. And then in this case, liquid, or not in this case, liquids we don't say break apart. Our only liquid is water, and we consider that to be a compound. It is not aqueous. And so we just leave our water like that. We're not breaking apart into ions because it's not an aqueous solution. And when we go through and do a net ionic equation, we're meaning net meaning showing the overall change in the reaction. So what changed when we reacted our sulfuric acid and our sodium hydroxide? So before they were in 2 separate beakers, and now we poured them into 1 giant beaker. So what changed in this beaker? Well, I'm just going to go through and erase these quick, and then we will look at what changed between these. So in our left beaker we had our sulfuric acid, and here we had, and I'm just going to change colors, we had these H plus ions on the left, but we don't have them on the right because those hydrogen ions went from being aqueous to being liquid. So we can't cancel that out. We have aqueous sulfate on the left, and we have aqueous sulfate on the right, so that gets canceled out. We have 2 aqueous sodiums on the left, 2 aqueous sodiums on the right, so those get canceled out. And then this hydroxide changed states. It went from being aqueous in the sodium hydroxide to being liquid as water form. So to write our net ionic equation, all we do is carry down everything that did not cancel out. So we will now have 2 hydrogen ions that were aqueous plus 2 hydroxide ions that were aqueous have now produced, oh, and sorry, I should have had 2 up here, have now produced 2 waters that are considered to be in a liquid state of matter. And hopefully that was a good refresher for you on how to do complete and net ionic equations. This slide just gives some examples of how we properly name and write acids and bases. So you will notice that when we are going through and doing this, many of our acids will start off with something like hydro, short for hydrogen because they start with hydrogen, and then chloric for the chlorine, so we call it hydrochloric acid. And for the acids, you see if there's something like a nitrate in there, we just call it nitric acid. Sulfite is called sulfurous acid, and so on. Naming of bases is a little bit easier. So when we name a base, a lot of times it will just be like sodium hydroxide is written as NaOH, and we just write the sodium plus our hydroxide. Or we could have magnesium hydroxide, which would just be written as Mg OH2, because we have to balance our charges. Remember, magnesium has a +2 charge, hydroxide has a -1 charge, and this is just written as magnesium hydroxide.